Now, after calculation of the movement, we check the depth of the slab. The depth of the slab is checked by, now here we have to calculate the depth. Check for the depth. Now the check for the depth is given by d is equals to under root of mu max upon ru max into b. As we are considering the unit width, b is taken as 1000 mm. Mu max means value calculated from step number 7, and ru max is calculated from step number 2. From here, see here, from here the value of ru max is considered. Okay, then what is this check then? This check state that our d should be, this depth should be less than d provided, or in the other words we can say that d provided should be greater than the d required. Okay, here this d is also called as d required. Okay, then we, after this checking, giving the check, what we do is we calculate the AST of the section. Here ASTx is equals to 0.5 FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 MUx upon FCK BDx square. Note that BDx square b into dx. And now in the calculation of ASTy is equals to 0.5 FCK Fy into bracket 1 minus under root of 1 minus 4.6 MUy upon FCK BDy square b into dy. This is very important thing. Note here MUx dx square dx, MUy dy square dy, where dx and dy is equals to capital D minus depth of the cover plus thickness of bar. Here thickness of bar is given by, diameter of the bar. We are assuming that we are giving the generally the notation for diameter bar as a d, but as d notation is utilized very frequently at many times, so we do give here diameter of bar by f and divided by 2. Okay, and in the case of y, dy capital D minus dc plus f by 2 minus, again we are taking the f. This is the main difference while calculating the AST. Now what should be our check? This AST calculated should be greater than AST minimum. Okay, where now what is this AST minimum? This AST minimum in case of mild steel, it is 0.15 B into D upon 100, that is 0.15%, and for HYSD bar it is 0.12% of B into D upon for HYSD bar. Then after this we must assume the diameter of the bar and calculate the spacing. How to calculate the spacing? It is calculated in the following formula. Spacing S is equals to B into small AST divided by capital AST, and the spacing should not be greater than 3D or 300 mm. Okay. Now here small b is equals to 1000. Small ast is equals to pi by 4 into, suppose I have assumed the bar of diameter of 8 mm. Okay. Substituting this value into the formula, we get the spacing. Here we have to again see the note. What is that note? The main reinforcement shall be provided in the middle strip of size 3 by 4 Lx into 3 by 4 Ly at an right angle to the each other. Then we calculate the distribution steel ASD. ASD is equals to 0.15% of BD or for mild steel and 0.12% of BD for the HYSD bar. Here the spacing is calculated by the same formula, that is small b into small ASD divided by capital ASD. Capital ASD means this ASD. Okay. Small ASD means pi by 4 into area of diameter of the bar. Okay. And this ASD will be provided in a strip of width 1 by 8 Lx and 1 by 8 Ly. Then the next step number 11, that is the torsional reinforcement or the restrained corner. AST at the corner where slab is discontinued at the both the edges. Here that AST is equals to 3 by 4 ASTX. Then when the AST at corner where slab is discontinued at one edge, that AST is equals to 3 by 8 ASTX. AST is 0 at the corner where slab is continue over both the adjacent edges. This AST, here it is AST. AST means torsional reinforcement. This AST will be provided at the corner in the form of mesh at top and other at the bottom for a length of Ly by Lx by 5 by Ly by 5 parallel to the side of the slab in a U form. See how it will be provided? In this way, in the U form. Okay, in this U form. So how this reinforcement is provided? In this way. Okay, in the form of U form. Now the next check is the check for the deflection. This check for the deflection is given by D is equals to Lx upon L by D basic into alpha 1. The check is similar to all as our previous problems, and this alpha 1 is modification factor calculated from IS 4562,000, page number 38, figure number 4. From here we have to calculate the Fs. Fs is equals to 2.58 into Fy into AST required divided by AST provided. Then PT is equals to, that is the percentage of steel, is equals to 100 into ASTX provided divided by BD, and it should be less than PT assume. If my PT is less than PT assume, then my design is safe in the deflection. Then we go for the check in the shear. For the check of the shear, we calculate the VUX is equals to W into LEX by 3. Then tau VX which is equals to VU divided by BDX. If tau VUX is less than K into tau C, then the design is safe. Similarly, we calculate VUY which is equals to W into LUY into beta upon 2 beta plus 1. Then tau VY is equals to VUY upon BD into DY. If my tau VX is less than tau VY is less than K into tau C, that time the design is safe. No need to increase the depth of the slab. Now PT at the support, as we provide 50% bent up bar, PT is 50%. Alternate bars are bent up, PT provided is 50%. Tau C max from page number 72, tau C 73, V into tau C, therefore this design is safe. Lastly, we give the check for the development length. LD is equals to 1.3 M1 upon V plus L0, which is given on page number 42. Then LD is equals to 0.87 Fy divided by 4 times tau BD. Take M1 is equals to 0.87 Fy AST into bracket D minus Fy AST divided by FCK into B. V is equals to maximum shear. L0 is equals to Ls by 2 minus DC. So this is what the design steps for the design of two-way slab. Thank you.